So today's speaker, Professor Robert Mello from Huzhou University, China. So he's going to talk about the space of gauge invariant operators and finite. Please start.
So thanks very much. Thanks for the invitation to present the seminar. And it's very nice to be back in Korea. Okay, so the work that I'll be presenting today was reported in these 4 papers with Anton Levitsky, with Minkyu, with Jakub van Zyl, with Gareth Kemp, and with Anik Rudra. So we're going to be talking about the space of gauge invariant operators at finite n. So let me first of all try to motivate why this would be something interesting to consider. So this falls into the field of the ADS-CFT correspondence. So we have a conformal field theory that is dual to a theory of gravity. Inside the conformal field theory, the physical observables would be your space of gauge invariant operators. If you take a look at single trace operators that have a small dimension, so what you should think is a trace with a few fields inside the trace, those operators are dual to supergravity modes. So when you think about a graviton is dual to a single trace operator in the conformal field theory. If you have a product of multi-trace operators, this would be dual to a multi-graviton state. And at infinite n, these single trace operators have diagonal correlation functions. And this corresponds to the statement that in the Fock space, the overlap between different states in the free theory vanishes between different states. So the single traces diagonalize the 2-point function. If you go away from large n, these different states start to mix, and that mixing can be understood perfectly by gravitational interactions in the dual type 2b supergravity. So you really match perfectly the spectrum of Fock space states and the perturbative interactions between those Fock space states. If we're keeping n finite, then you can think about some operators built using n fields. So n is very large, but using n fields, we get something called a giant graviton brane in the dual gravity. And we know exactly how to represent these in the CFT. It's some complex multi-matrix operators known as Schur polynomials. If you consider operators now built using order n squared fields, you get the so-called Lin-Lunen-Maldacena geometries, the LLM geometries. These have a dimension of order n squared. And what I want to point out is we've just discussed perturbative excitations about the vacuum, single Kaluza-Klein gravitons. We've discussed giant gravitons, which are branes, something like a soliton in the string theory. And we've discussed an LLM geometry, which would be a new background in the string theory. All of these different objects are dual to the space of gauge invariant operators. So what the space of gauge invariant operators in the gauge theory is reproducing is the Hilbert space of the holographic gravitational theory. So by studying the space of gauge invariant operators, I'm learning about the Hilbert space of quantum gravity. I want to do it at finite n. So what does that mean? Well, I'm going to start off by just thinking about a single n by n matrix where it's simplest to think about the ideas. This matrix will have a gauge symmetry with x transforming in the adjoint of the gauge group. And at n is equal to infinity, if you say, well, what is the space of gauge invariant operators? Its traces of powers of x, these variables called phi k. And we say that the phi k freely generate the space of gauge invariant operators. By generate, I mean every gauge invariant operator can be written as a polynomial into phi k's. And by freely generate, I mean there is no equation relating phi k's for different values of k. At finite n, the big difference is there are now trace relations. So this equation sitting over here is true for any 2 by 2 matrix. So it's an absolute identity for any 2 by 2 matrix. But what does it mean? It means 2 phi 3 minus 3 phi 2 phi 1 plus phi 1 cubed is equal to 0. So it's no longer true that our phi k's are free. They now obey some equation. So how does this affect the space of gauge invariant operators? Well, it turns out that because of trace relations, we don't need all phi k's. We only need phi k from k going from 1 to n, and that generates the complete space of gauge invariant operators. So I would like to know, how do these trace relations affect the Hilbert space of the quantum gravity. By the way, we know that the gravitational coupling is 1 over n squared. So let me put that up. So G Newton is 1 over n squared. So as soon as I'm thinking about finite n, I'm thinking about strong gravity effects. So this is something that should be there at strong values of gravity, and that's exactly where we expect the ADS-CFT correspondence can teach us something.
So,
Yep.
So for finite n, let's say n equal to 1,000, then there's a relation up to 5 to 1,000 powers. But if I am paying attention to somewhat much less, like up to 900, then I may get essentially less and less effect of that extra.
Absolutely. So this effect will kick in when you have n plus 1 matrices. So over here we had n is equal to 2. It was when we had 3 matrices. Mm-hmm. And we'll actually talk about exactly how all of these trace relations are derived. Yeah.
So by taking n goes to infinity limit, essentially that relation will be away.
Absolutely. The structure of the gravity Hilbert space at n is equal to infinity, so that would be, for example, the Fock space of supergravity and things like that. It's very, very different to the finite n Hilbert space. And we'll see the differences. Yep. Okay. So, by the way, for this one matrix case, we know the answer and it's well known. But when you have more than one matrix, and I'm going to consider the case of D matrices, it's simply not known how to take finite n into account. So we've now got D of these matrices, each transforming in the adjoint of the gauge group. What is the space of gauge invariant operators? We'll take the space of all independent single traces, and they again freely generate the entire space. And I want to know how is this description modified at finite n? And this is really the contribution of our work to answer this question, which wasn't known before our work. Okay, so let me give you an outline of the talk. I am going to use invariant theory. It's very technical, so I'm not going to go through invariant theory in details. I'm going to do it just by counting. And by counting, you'll be able to see exactly what are the theorems that I'm using and exactly how they work. Once I've done that, I'm going to tell you the result that we proved. Then I'm going to give you a careful problem statement, which I'm going to solve for one matrix and use with the help of the Moline-Weil formula for 2 and 3 matrix models. So I'm going to argue in these sections 3 to 6 that the statement that we've got here is correct. And I'm going to try to convince you of the statement that we found. And then finally, I'll tell you what general lessons we get from this work. Okay, so now for the counting problems that come from invariant theory. So I'm going to start off by saying how many degree D polynomials can we construct using 2 variables, x and y? So for example, if I was at degree 2, I could have x squared, xy, and y squared. So there's 3 degree 2 polynomials. That's the counting that I'm after, or 4 degree 3 polynomials. How do we count this? Well, if you take 1 over 1 minus x times 1 over 1 minus y, expand each of these factors, and then multiply out the 2 brackets as usual, what you'll notice is I'm generating in this last line all of the polynomials that appear on that list, and I generate them all exactly once. So you can see there's a 1, xy, x squared, xy, y squared. And here we've got a 1, xy, x squared, xy, y squared. So we're just generating all of the polynomials that we've listed exactly once. Okay, now, if we just want to count, we can say x is equal to t is equal to y. And then, for example, x squared, xy, and y squared becomes 3t squared. And that 3 multiplying the t squared is telling us there's 3 degree 2 polynomials. This function, 1 over 1 minus t squared, is called a Hilbert series. This is something introduced by David Hilbert. And what it is, if you take this function in power series expanded, the coefficient Cn of t to the n counts how many degree n polynomials you have. And what you can see is I was generating the polynomials using x and y, and you can see that there's a 1 over 1 minus x, 1 over 1 minus y. So in the Hilbert series, each of these factors in the denominator, there's 1 for each generator of our ring. And that's something that you'll see again and again. So it's worth paying attention to. Let's generalize this a little bit. Let's say I had two generators of degree 1, one of degree 3, and one of degree 4. What then does the Hilbert series look like? There's a 1 minus t squared for the two degree 1 generators, one generator of degree 2, and one generator of degree 3. And if you expand out this Hilbert series again as a power series, Cn counts how many degree n polynomials you have. Now, the counting problems that we've done so far have been a little bit artificial because they're called freely generated. Well, not artificial, but special. So these counting problems do appear, but they're not the most common. The most common counting problem is counting with constraints. So imagine you wanted to count the spherical harmonics. So we're going to count spherical harmonics in d dimensions. What should you be doing? You should count degree n polynomials constructed with x1 up to xd. Now, I've told you there should be a factor in the denominator for each generator of the ring. Here we've got d coordinates generating the ring, so you might have thought we should have 1 over 1 minus t to the d. That guess is wrong. Why is it wrong? It's because, for example, think about angular momentum 0. 1 is angular momentum 0, but the sum of the squares is also invariant under rotations, so the sum of the squares is also angular momentum 0. So when I'm counting spherical harmonics, I shouldn't count the sum of the squares as different to 1. One way to correct for that overcounting is impose this equation amongst the generators. Now we don't have free counting because the generators obey a constraint. And it's not just this equation that you have to impose. Any polynomial multiplied by the sum of the squares should not be counted as distinct from that polynomial. So how do we take it into account? We've overcounted. To correctly count, we need to subtract something off. That's why there's a minus t squared in the numerator. So the minus is to correct for the overcounting, and it's t squared because the constraint we need to impose is degree 2. The good news for today is actually we'll only have to deal with free rings and free algebras, but we need one more generalization. This is the last counting problem I'm going to look at. This is the most important. So how many degree d polynomials can I construct using x and y freely? So x and y to any power. And then I must use 1 and exactly 1 of 1 w squared or v cubed. So the first term is everything that can be constructed from 1 and any polynomial in x and y. Then I've got w squared times any polynomial in x and y, and v cubed times any polynomial in x and y. And if I again expand that out, you'll see I've constructed all polynomials that I can exactly once according to the rules that I specified above. So again, setting all of these variables equal to t and expanding, the coefficient 7t cubed tells me there's 7 polynomials of degree 3. So that's what the Hilbert series looks like now. This is what I want you to remember. We had one type of generator, that's corresponds to the numerator, the 1, the t squared, the t cubed, and that's the 1 w squared and the v cubed sitting there. So the numerator encodes the generators that I'm allowed to use exactly once. I can use it once and I must only use one of them. So those are encoded into the numerator of the Hilbert series. The x, y, these can be raised to any powers. Those are the generators that act freely, and those are encoded into the denominator of the Hilbert series. So if I show you a Hilbert series, the numerator is telling you about generators that act most once. The denominator tells you about generators that act freely. So we've spoken about Hilbert series. What does this have to do with physics? So now I'm going to show you what it has to do with physics. So let's think about a partition function for a multi-matrix oscillator. So if you want to calculate this partition function, what would you do? Well, you'll take a sum over states, e to the minus beta times the energy of each state. This is an oscillator, so I can find the states and energies like I always do. I introduce a creation operator. Now I'm dealing with a matrix model, so both XA and the momentum are matrices, but that's no problem. We can do that. So A dagger will be a matrix. To form any eigenstate, I have a polynomial in the A daggers acting on the vacuum. So what's important here? For each state, I have a polynomial. So when I'm summing over states in the partition function, I might think that I'm summing over polynomials. The other thing is I don't have to have a single trace here. I want a gauge invariant operator, which means that all indices must be contracted, but it could be a single trace, a double trace, triple trace, whatever you like. So for every state, there's a polynomial. Now let's imagine I've subtracted off the ground state energy of my oscillator, and each A dagger adds an energy of 1 to the state. Then the energy of the state is just the number of A daggers, which is the degree of the polynomial. So when I look at the partition function, which is the sum over states, is actually a sum over polynomials. And I should weight the different terms by e to the minus beta times the energy, or x to the degree of the polynomial, where x is equal to e to the minus beta. So what I'm actually doing here, I'm summing over polynomials, and for each polynomial of degree n, I'm weighting it with x to the n. But that's what our Hilbert series was. So this mathematical object that we studied is actually the partition function of a harmonic oscillator. So if I show you a partition function of a harmonic oscillator, you should think in terms of a Hilbert series, and you should take the lessons that you learned from the Hilbert series. So now let me tell you the results that we found. For all of these multi-matrix models, this is the form of the partition function for these multi-matrix oscillators. The numerator is a sum of terms that are all positive, all with positive coefficients, and the denominator is a product of factors. Well, thinking in terms of the Hilbert series, and I want you to bring, oh, sorry, wrong way. I want you to bring this picture into the mind, sum of positive numbers multiplied by a product of factors. That's exactly what we have here. Sum of positive terms of x to the I multiplied by a product of factors. So each term, each factor in the denominator corresponds to one of the generators that acts freely. In invariant theory, these are called primary invariants. You can act with those freely. Each term in the numerator, you act with it once, and exactly once. That's called a secondary invariant. The primary invariants are always single trace operators, and if you're looking at the term 1 minus x to the j, the corresponding primary is degree j. There's j matrices inside the trace. If you've got a term in the numerator which is x to the I, the total degree is I, but in general, it's a complicated multi-trace operator. And you'll see examples of this as we continue. So the space of all gauge invariant operators takes this structure. The secondary invariants act once and only once. There's a product of the primary invariants. They can be raised to any non-negative integer power. And the thing that's very important is this direct sum over here generates every state in the space of gauge invariant operators, and there's no redundancy. Each of those states is linearly independent. Okay, and that's the structure that you see from this partition function. This is a mathematical fact. You cannot have a problem with this. It's the result of a theorem. I'm not going to give you a physical interpretation.
So the numerator seems to be some kind of constraint, while the denominator is.
So let me tell you how we interpreted it. Not in terms of constraints, but we interpreted it as follows. There are constraints, and we'll come back to those. The way that we interpret it, this is just a mathematical result. Here is our interpretation. So take a look at what you've got. In each term, you've got an S1 and S2, or whatever, some other secondary.
Okay. In the previous page.
Yes.
So you introduce only single variable x, right?
Yes.
And the sum over all the states.
Yes.
So eventually the partition function z is a function of what? So in the C.
Just x, e to the minus beta.
And also CIS and CJP, those should be given in advance.
So for a specific D set of D matrices, you can calculate those. Those are a property of the Hilbert space. So those coefficients are determined by saying, here's the full space of gauge invariant.
So some dynamics will determine those numbers.
Actually, not even dynamics, kinematics.
Oh, I see.
Yeah. So those will all be determined, and you'll see what they look like soon.
So only the x is the variable.
That's right. So this is just a partition function, no other fugacities turned on, just a temperature. Yeah. Okay, so this is a mathematical fact, but here's our interpretation. So what does this look like? So these blue, the primary invariants that we can raise to any power, what does that look like? Those look like creation operators inside a Fock space. So we want to interpret the primary invariants as perturbative degrees of freedom. And I'll build up evidence for this. The other thing that we want, you see, if you give me the vacuum, I can put any number of Fock space excitations in the vacuum. So that's like this term over here. Then if you give me a soliton, I can put any number of Fock space excitations on top of the soliton. So S2 is behaving like a soliton. or a new background. If you give me a new supergravity background, I can put any number of Fock space excitations on that new supergravity background. So I want to interpret the secondary invariants as the non-perturbative states of the theory, either new backgrounds or solitons or something like that. And I want to interpret the primary invariants as perturbative degrees of freedom. How much evidence can we find for that point of view? That's what I'm going to try to convince you of as the talk goes on. Okay. So let me tell you the actual problem that we solved carefully. So we studied this Hamiltonian. It's a trace of momentum squared plus trace of position squared. So that's just a normal oscillator. Quantized as usual. There's a commutator between momentum and position. Few more indices because these are matrices, but nothing too radical. And then both the position and the momentum transform in the adjoint of the gauge group. And then you say, well, what's the complete space of gauge invariant operators? It would be traces of any product of x's. And I want to know, how do I describe the space of gauge invariant operators completely? What would I consider a satisfactory answer? If you give me a set of generators for this space, and you tell me the algebraic structure of those generators. Do they obey some constraints? Do they not obey constraints? Something along those lines. Okay. So let's see. Great. Good. Okay. So here's a warm-up for the one matrix model. So I just told you what the partition function is. Soon I'll give you the formula that we actually use to calculate that partition function. But for one matrix, there's one A dagger. That's what the Hamiltonian looks like after I subtracted off the ground state energy. Go ahead, calculate the partition function. That's exactly the form that it takes. Thinking about this as a Hilbert series, this algebra of invariance, ring of invariance, is generated by a total of n generators. And this makes sense. This is this trace of x to the k, where k goes from 1 to n. So this answer is consistent with the partition function, but the partition function certainly doesn't prove this answer. How do we prove that those really are the invariants? And the way that we prove it is by using the trace relations.
So far, this X is just one by one simple harmonic oscillator.
This is just a simple oscillator, matrix oscillator, yes.
Why did you say so one matrix?
Because we're dealing with one matrix degree of freedom.
One means it's just one capital X matrix.
Capital X, n by n matrix.
N by n matrix.
N by n matrix, exactly.
But here is a one by one.
No, here it's an n by n.
Oh, I see.
That's where the size of the matrix sets the generator. If it was just a normal oscillator, just one p and x, the partition function would just be 1 over 1 minus x. Now it becomes a little bit more complicated because it's an n by n matrix, so you get n of these factors. And they can act freely. Now, so the way that we prove this answer, so not by looking at the partition function can suggest what the generators are. The way we prove these are the generators is by looking at the trace relations. And the mathematicians have given us a very efficient way to think about trace relations. It's really the work from Prochesi in the mid-70s. He's an invariant theorist. And I'm going to tell you what the trace relations are just for 2 by 2 matrices, and n by n is a very simple generalization. So let's look at 2 by 2 matrices. In this case, the trace relations are 2 plus 1 factorial, so 3 factorial, so 6 terms. And there I've written down 6 terms. Now let me tell you how we get them. So take W1, W2, and W3. These are all 2 by 2 matrices. Now, down the 2 by 2 matrices sitting in the first term there. Now, what I'm going to do is I'm going to take the column index, so the second index of each of these matrices, and I'm going to anti-symmetrize over those indices. So the first thing I could do is swap I1 and I2. If I swap I1 and I2, put in a minus because I'm anti-symmetrizing. I could also swap 2 and 3 with a minus, or swap 1 and 3 with a minus. Then I could first swap the indices of W1 and W2, and then swap the indices of W2 and W3. That'll be a plus because I've done 2 swaps. And for the last term, I could first swap the indices of 2 and 3, and then swap the indices of 1 and 2, and again, that'll be a plus. Now I've totally anti-symmetrized those 3 indices. I've anti-symmetrized 3 indices that each take 2 values. I have to get 0. So this is equal to 0. And it'll be 0 for any value of I1, I2, and I3, and it'll be 0 by sum over I1, I2, and I3. So if I sum over I1, I2, and I3, I get an identity between different traces. And that's where all of the trace relations come from. What did Procesi's theorem prove? It proved that if you take the W's and you construct them using a single matrix, you get all of the trace relations for a single matrix model. So you can make different choices for W1, W2, and W3. They're just any arbitrary matrix built out of a single matrix. So you could basically take that matrix to powers. If you have D matrix model, the W's could be any products of the matrices. And taking those relations together, this generates the complete set of trace relations for the D matrix model. Now, something that I want to point out is this identity is true regardless of the potential in the CFT, so how the matrices are interacting, regardless of coupling strengths or anything like that. The only thing that this identity depends on is the value of capital N. So if you tell me capital N, I can write down the trace relations. I don't even need to know what is the interaction. And that equation will always be obeyed. Now let's go to N by N matrices. Well, it's a trivial generalization. Now you take N plus 1 matrices, which are each N by N, and you do the same thing. Write them down, anti-symmetrize over the column indices. If I've anti-symmetrized N plus 1 indices that each take N values, the answer is 0. So again, I'll get a naught. And Procesi actually proved his theorem for this more general case of any N. This equation will generate all of the trace relations. So whenever we talk about trace relations, this is what you've done. And that's it. There's nothing more than trace relations.
In the 2 by 2 case, it's more understandable. In N by N, we have N squared degrees.
We have N squared degrees of freedom, but you see, we're anti-symmetrizing N indices, and each index runs from 1 to N.
So much more.
So if you anti-symmetrize K plus 1 indices, each of which takes K values, you're going to get 0. And that's actually the concept of the theorem. Actually, so Procesi is really credited for this, but Hilbert wrote that down in his book. He didn't explain it, but he had that statement. And by the way, just one other comment. We haven't swapped the position of any matrices here. So they could have been normal bosonic, or they could have been Grassmann matrices. So this is also how you generate the trace relations if you have fermionic matrices. There's no difference. So this really is a completely general description of the trace relations, and so simple. Okay, so now let's see how we use the trace relations. So I've written down the trace relation for at n is equal to 2. So this is the simplest. So at n is equal to 2, there's the trace relation. And now I'm going to choose W1 to be x to the k, W2 to be x, and W3 to be x. What does this equation become? Well, I can write it in terms of my invariance by k, and that's the equation. Now, if we plug in k is equal to 1, the last term becomes phi 3. Every single other term is either a phi 1 or a phi 2. So I can solve for phi 3 in terms of phi 1 and phi 2. If I then plug in k is equal to 2, I'll get a phi 4. When I solve for phi 4, this is what I get. But I know phi 3 in terms of phi 1 and phi 2. So I can also express phi 4 in terms of phi 1 and phi 2. And I can just keep going in k. And in the end, I can express every single phi k with k greater than or equal to 3 as a polynomial in just phi 1 and phi 2. And this is the proof that, in fact, phi 1 and phi 2 are needed to generate everything. And you can see this equation cannot possibly determine phi 1 and phi 2 because you have to plug in at least k is equal to 1, and then phi 3 starts to appear. So phi 1 and phi 2 really are independent. You can't determine one in terms of the other, but everything else can be determined in terms of the phi k's. This is always going to be my logic. I'm going to calculate the partition function, use it to guess a set of invariants, and then use the trace relations to prove that they generate everything. Because the proof based on the trace relations doesn't depend on the interaction or the coupling strengths, I get very general statements about the space of gauge invariant operators not tied to the oscillator. I calculated the oscillator to make a guess for what the generating set of invariants was, but my verification is completely general. Okay. So now I want to go to more than one matrix, so I need to use the Moline-Weil formula. So let me just tell you what's going on here. So we want to calculate the partition function. I'm going to imagine I'm dealing with D matrices. So I've got D A daggers. I've got a 1 dagger for the first matrix, a 2 dagger for the second matrix, up to a D dagger for the Dth matrix. I want to sum over all states. I can raise A1 dagger to the N1, A2 dagger to the N2, and so on. So if I sum over all of these N's that I can raise each A dagger to, I'm actually summing over all possible states. For each A dagger, I've got a contribution to the Boltzmann factor. This is this x to a power, that's all contribution to the Boltzmann factor. And then I have to calculate the number of times the singlet appears. So how many singlet states do I have of this energy? I'm going to do that with a character sum. So I've written the character formula here. Maybe it's not too important that I go through all of the details. One thing that is important, I land up with an integral over the group UN, but the integrand depends only on characters, so only on eigenvalues. So I can reduce this to an integral over just the eigenvalues. One of those integrals is trivial, so I'm left with an integral over n minus 1 eigenvalues. If you now tell me the value of D, how many matrices we're talking about, you tell me the value of n, that these are n by n matrices, then this formula has a completely explicit integrand. All I need is D and n, and then I know the integrand. I can go ahead and calculate this integral. We're talking about a unitary matrix. Unitary matrices obey U, dagger U is equal to 1, and that means that the eigenvalues must lie on the unit circle. So all of these integrals are run over the unit circle. So I can do these integrals just using the residue theorem. I know exactly what the contour of integration is. I just need to know where the poles lie. And I know that x is equal to e to the minus beta, so x is less than 1. So it's completely unambiguous where the poles lie. And I just now apply Cauchy's residue theorem. This is what you get for n is equal to 2. That's what the partition function looks like. I've graded things a little bit. I introduced a fugacity, so I've got x1 and x2, I've called them x and y, and then I introduced a chemical potential for x and a chemical potential for y. When I work out what the partition function is, that's what it looks like. This partition function is a 1 at the top times a product of 5 factors. Thinking about this as a Hilbert series, this space is generated by 5 invariants. And looking at the grading of these different invariants, it's very easy to guess what the generators are. So that's my guess. So for example, x5, I would guess is trace of x times y. It's just a guess. Now what I'm going to do is I'm going to take the trace relations and I'm going to prove that using these 5 generators and the trace relations, I can construct every single gauge invariant operator. So what do I have to do? You give me any gauge invariant operator and I'll tell you what trace relation you need to use to solve it. And then you'll be able to work out what that gauge invariant operator is. So let's look at traces of 3 matrices. I'll just give you one example. So I'm looking at constructing an invariant using nx matrices and my matrices. If I choose m as 2 and n as 1, so I've got 2 y's and 1 x, and I look at the trace relation obtained by setting. So the trace relation was a function of these 3 matrices, A, B, and C. If I set where are we? If I said A is equal to X, B is equal to Y, and C is equal to Y, that's the trace relation that I get. And I can express the trace of X, Y in terms of these traces here. Each trace has at most 1 matrix, at most 2 matrices in it, or 1 matrix, and all such matrices are included in our generating set. So, for example, the trace of xy squared is that in terms of our generating set. And again, just using trace relations, we can work out what is the trace of yx squared, the trace of x cubed, and the trace of y cubed. So with 3 matrices in the trace, we've expressed everything in terms of that generating set. If you go to 4 matrices, now you see a new effect appearing. So let's look at an operator built with 2 y's and 2 x's. Now we can get 2 independent gauge invariant operators. We can have the trace of x squared, y squared, or we could have the trace of xy, xy. Well, luckily for us, there's 2 independent trace relations. We can set A equal to y squared, B equal to x, and C is equal to x. That tells us what the trace of x squared, y squared is. Or we could set A equal to xy, B equal to x, and C equal to y. And that trace relation tells us what the trace of xy, xy is. But the point is, will there always be a sufficient number of gauge invariant operators to determine all, a sufficient number of trace relations to determine all gauge invariant operators? And in fact, we proved, yes, that is the case. So I'm not going to...
xy and yx is more or less equivalent or very different?
So X is a Hermitian matrix, Y is a Hermitian matrix. If
So they are different, right?
Yep.
Not commutative. So
Exactly.
T2,
Yep.
why, what made you choose xy rather than yx?
Oh, this was just pure experimenting, if you chose yx in this particular case, it would also have given you a trace relation that would determine trace xy. Yeah, so I could, if I had chosen this to be a yx, it would also have worked. Yeah, just what's important is it's not a single matrix squared. And now if you go up to operators of greater length, so let me just say we proved this by induction. I can tell you exactly which trace relation you need to determine all operators, but by induction we gave a rigorous proof that tells you that every single gauge invariant operator is determined in terms of that generating set. You know, one way to think about this, if you've got a 2x2 matrix, and you say to me, what's the basis independent information in that 2x2 matrix? Well, there's two eigenvalues, so that's easy to answer. Now, let's say I give you two matrices, and you say to me, well, what's the basis independent information in these two matrices? So that's a harder question to answer, because you can diagonalize one of the matrices, but the other one will not be diagonal. What's the answer to that question? The answer to that question is these 5 invariants. So those 5 numbers over there tell you all of the basis independent information in just two matrices. Okay. So for two matrix models at n is equal to 2, we've proved that all gauge invariant operators can be written in terms of these 5 generators.
So that kind of relation can be generalized to any n, or so in the one case is more trivial, just eigenvalues.
Yes.
And the two, are those somehow related to the eigenvalues? It seems to be very.
No. So for n by n matrices, I'll show you some results, and you'll see it's a highly non-trivial generalization. We'll talk about how it generalizes.
Not very systematic.
There are some systematics, but it's complicated. Yeah. So at this stage, what have we learned for this 2x2 two matrix model? So our argument that the Hilbert series computes a partition function holds only for the oscillator. So it's only the oscillator partition function that will be Hilbert series, but the fact that these generate the complete space of gauge invariant operators is a general fact for any potential that you have in your multi-matrix model. It's a completely general fact. Okay, now let's look at 3 matrices at n is equal to 2. We've got 3 matrices X, Y, and Z. I've again graded it into the chemical potential for each. And the reason why I wanted to do this is the first time where you see a non-trivial secondary invariant. So that X, Y, Z, there's a non-trivial secondary invariant. This is something that you should use exactly once. And Bamgun, this comes back to your question, are there constraints? Because why is it that you're only allowed to use X, Y, Z once? So we can read off the generating set, the primary invariance, that's fine. And this is our guess for the secondary invariance, which turns out to be true. But if you take the trace of X, Y, Z and square it, that doesn't look 0. It looks perfectly fine. So why do you exclude it? The answer again comes from the trace relations. Using only the trace relations, you can prove this identity. S squared plus S times a polynomial in the primary invariance plus 1 times a polynomial in the primary invariance is equal to 0. So if you want to get the operator S squared, you've already got it if you've got things that are linear in the secondaries and with arbitrary coefficients that are polynomials in the primaries. So you don't include S squared to avoid redundancy.
So if you change the rather than X, Y, Z or cyclic one, but the acyclic one like X, Z, Y, then the relation will be changing a little bit.
So if you had, so you can take any cyclic permutation, that's fine.
Then yeah, that's true.
But for example, if you took this, if you took the trace of X and maybe you put in the commutator of Y and Z, any other operator that you can think of can be expressed linearly in the secondaries with coefficients that are arbitrary polynomials in the primaries. So any other operator that you think of writing down can be expressed in terms of these, and there's no redundancy. That's what we mean by freely generated. So we've really got a complete description of this Fock space. Okay, so what is the complete space of gauge invariant operators? You're allowed to take these 9 primary invariants, raise them to any power, times 1, or the 9 primary invariants raised to any power times S. So it's natural to think of the first term as a space of perturbative excitations of the vacuum state created by the identity, and the second term as the perturbative excitations around some soliton. Okay, so now let me just talk about how general these results are, and then let me tell you how we got evidence for that interpretation. So all of the partition functions that we've calculated take this form.
But the soliton can be not only one, but many solitons.
That's absolutely true. So you can have many solitons, but there's actually a cutoff on the number of solitons. And that cutoff, that comes, in fact, in the complete Hilbert space, there's a cutoff on the number of solitons. And this is a property of gravity, and it's because gravity has these huge redundancies in it. So I'll be talking a bit more about that in a moment. There's an emergent cutoff on what you would have thought of as naive low energy degrees of freedom. This is needed if you want to improve the UV behavior of gravity. And we claim that the trace relations, I don't know if it accomplishes it all on their own, we don't have an answer to that yet, but certainly it helps to improve the UV behavior. Yeah. Okay. So the fact that the Hilbert series takes this form is something in invariant theory called the Hironaka decomposition. And this is actually the Hilbert series of the ring CND of GLN invariants. We can think UN invariants, there's no difference in the invariant ring, of Dn by n matrices. This language comes from invariant theory, that the denominator encodes the primary invariance while the numerator encodes the secondary invariance. Maybe just a little fun fact, Hironaka was a MSc student at Kyoto. He discovered this result. It was left in his MSc thesis that he decided not to publish. He went on to Harvard and won a Fields Medal and all of that. But his supervisor wrote a very influential book on algebras and rings, and he's the one that wrote up Hironaka's MSc thesis, and he called it the Hironaka decomposition. So I thought that was just a little bit of interesting history. The number of primary invariants, which equals the number of denominator factors, is called the Krull dimension of the ring, and it's been calculated to be d minus 1 times n squared plus 1. And now I just want to mention a few things because this is kind of important for you to get an idea of how general these results are. So our partition functions all take this Hironaka form, and that's what's driving everything that we've done. So how general is this? It turns out that whenever your algebra is Cohen-Macaulay, you will have such a description. Now, what does it mean for an algebra to be Cohen-Macaulay? So let me tell you the abstract definition. So algebras have something called the Krull dimension. What the Krull dimension is, it's the maximum number of algebraically independent elements. So think about our ring with x and y. X and y are certainly algebraically independent. I can't write x in terms of y. I can't write y in terms of x. But anything else, x squared or xy or y cubed, these can all be written by multiplying x and y's. So the Krull dimension for that ring with just the x and the y would be 2. For these matrix rings, you find out the Krull dimension, the maximum of algebraically independent elements, is d minus 1 n squared plus 1. Now, there's a second way to measure dimension of rings and algebras. So in algebraic geometry, you try to replace all of geometry by algebras. So what's a good definition for dimension? And it's called the depth of the algebra, or the depth of the ring. So what's the idea? We're in 3 dimensions. How many equations can I impose independently? Well, I can say z is 1. Now we're at the surface of the table. Then I can say y is 1. I've drawn a line on the surface of the table. And now I can say x is 1. I've drawn a line in this direction. I'm at a point. I cannot impose any other equations. Now I'm at a point. I've fixed where I am. The depth of an algebra or a ring is the maximum number of independent conditions you can impose. A Cohen-Macaulay algebra or ring is one for which the depth equals the Krull dimension. So what does that mean? Probably you don't have much intuition for that, but let me make the following observation, and this is where the intuition should come from. If you look at free algebras and free rings, these are the ones whose generators don't obey any constraints. So these are the simplest kinds of algebras and rings. Every single free algebra and free ring is Cohen-Macaulay. But there are some Cohen-Macaulay rings and algebras that are not free. So the Cohen-Macaulay rings and algebras is the biggest set. You've enlarged the set of free rings and algebras, but it's the biggest set that enjoys all of the nice properties that free rings and algebras do. And what's one of those nice properties? That it admits a Hironaka decomposition. So the question you're really asking mathematically is our algebra of invariance Cohen-Macaulay or not? And there's a theorem called the Rochester-Roberts theorem that tells you if you're studying invariance of a linearly reductive group, the algebra of invariance is Cohen-Macaulay. What does linearly reductive mean? Pick up any finite dimensional representation of the group. Is it completely reducible? Then the group is linearly reducible. So all of the groups that we like in physics, okay, normal physics. I'm not talking about the exceptional groups. Unitary group, SO, SP, those are all linearly reductive. For the exceptional groups, I don't know which way. I haven't studied those, but usually people ask, is this true for the exceptional groups? I don't know. It's true for SO, SP, UN, SUN. All of those would be linearly reductive. The structure that I'm discussing here would be true for all of the normal gauge groups that you consider. So it's a very general result. Okay. So now let me show you some experimental results. So we took that integral equation. We evaluated the partition functions. So we're dealing here with two matrices. So inside this formula, D is 2. So we've got n squared plus 1. And then we just calculated partition functions. So look at this. 5. 5 squared plus 1 is 26. That's the number of primary invariants. 7. 7 squared plus 1 is 50. That's the number of primary invariants. So good. That's giving us the Krull dimension. Then we counted the number of secondary invariants. Now look, the primaries go 5, 10, 17. Modest grows up to 50. Now look at the secondaries. 1, 2, 64, 15,000, 312 million, 21,000 billion. This is a much faster growth than anything linear in n. What's going on? Now, we conjectured that the secondary invariants should be dual to non-perturbative states and backgrounds of the theory. For these matrix theories, many of them have a dual that includes a black hole. And when you think about a black hole, what did Hawking and Bekenstein teach us? The entropy should be the area of the horizon over G Newton. And G Newton looks like 1 over n squared. So it should be n squared times the area of the horizon. If you want to explain this entropy, what dimension should your Hilbert space have? Well, it should be e to the entropy. So the dimension of your Hilbert space should be growing like e to some constant times n squared. And if you just try to fit a function to these numbers, e to an order 1 number times n squared fits remarkably well. It does look like e to an order 1 number times n squared. So it does look like most of the secondaries we would now conjecture would be microstates of a black hole. Can we actually prove this? And it turns out, yes, we can.
So here, capital N is the size of the matrix.
N by N matrix. I've only got 2 matrices. Already when N is 7, that's the number of secondary invariants that you need.
But if the degree of freedom is really related to n squared, then even Coulomb degrees is n squared, right? And we have the
Well, you have to count gauge invariant operators. So for example, if you think about a single matrix, you'd say, oh, there's n squared matrix elements. So you'd say, oh, it looks like an e to the n squared. No, in that case, you don't get an e to the n squared. What you get is 1 over 1 minus x, 1 minus x squared, so on, 1 minus x to the n. What is the reason why our sort of common sense intuition goes wrong? It's because of gauge invariance. You must count things that are gauge invariant, and you must count things that are independent. And those are the 2 things. So here we count gauge invariance. And to get these numbers, what did we do? Take the space of all gauge invariant operators and completely solve the trace relations. These operators now are a space where there is no relations between the different operators, so you can really think about them as a basis for a Hilbert space. Okay?
So gauge invariance even changes the power and
Sure.
to the somewhat smaller.
Absolutely. Yep. Okay. So now what we did was we actually constructed all of the oscillator eigenstates that you would be summing in the partition function. And those states are labeled by 3 Young diagrams and 2 multiplicity labels. The Young diagrams, if we're constructing operators using NA1 daggers and MA2 daggers, the first Young diagram is n plus m boxes, the second n boxes, the third m boxes. But there's also these multiplicity labels. Now, the multiplicity labels run over values for a fixed n and m, and they run from 1 up to the value of the Littlewood Richardson number. So if you work out what the partition function looks like, it's a sum over these three Young diagrams. All of the multiplicity states have the same energy, so you can just sum over the multiplicity labels, and you get a square of the Littlewood Richardson number times by x to the n plus m. Now, why is this a useful rewriting of the partition function? It's because in 2019, Pak Panova and Yelyusov were able to estimate what's the biggest Littlewood Richardson number. And the biggest Littlewood Richardson number in their paper is equal to, if n, m, and n plus m are scaling like alpha times n squared, the biggest Littlewood Richardson number is e to the alpha n squared log 2. So what I can do is I can produce a lower bound for the partition function by saying, let me just sum the biggest term. It's meant to be a sum of all terms. Let me just sum the biggest term. So if I just sum the biggest term, I get this lower bound for the partition function. It turns out this is a great lower bound because, in fact, the partition function is being dominated by a single term. So this is actually a very, very tight lower bound. If you want to improve it, you better add order n's in the exponent. But this is a very, very tight lower bound. So now I've got a lower bound for the partition function. Now what I'm going to do is I'm going to look at the contribution coming from the primary invariants. And I'm going to see that the primary invariants can't possibly even give me the lower bound of the partition function. And because the primary invariants can't give me the lower bound of the partition function, I know the secondary invariants must be contributing something, and then I can estimate what the secondary invariants contribute. So this is the contribution from the primary invariants. This is a partition problem. What is this integer counting? It's counting the number of ways of partitioning x to the alpha n squared into pieces xj. So if I go ahead, actually this problem is too difficult to calculate because I don't know what the CJPs are, but I can overestimate the contribution from CJP. And I overestimate it by making parts smaller the whole time. So if I'm trying to break something into pieces and each piece has a length of 1, there'll be many ways to do it. If each piece is a length of 3, there'll be fewer ways to do it. So I've made each part in this partition smaller, and this gives me an upper bound for the contribution from the primaries. And the upper bound from the primaries is smaller than the lower bound from the partition function. So to make up for that difference, the secondaries have to contribute. And how much do they have to contribute? E to an order 1 number times n squared. So this growth, for the number of secondaries, we have established rigorously. That is how the number of secondaries grows. Okay. So the number of secondaries grows as e to the constant times n squared. But this is only possible if almost all secondary of invariants have a length of order n squared. Now, if you remember my first slide, I was saying that the LLM geometries, those are operators with a dimension of order n squared. You have roughly order n squared fields inside the operator, and those corresponded to new space-time geometries. The generic secondary invariant will correspond to a new gravity background. So this is very strong evidence for the proposal that we are making. And then, as I mentioned, the number of secondaries rarely reproduces the entropy that you would expect of a black hole. The other thing that's kind of interesting is as you increase n, the character of an invariant can change. So if you're at one value of n and it's a secondary invariant, as you pick up n, it can transition to become a primary invariant. So at one value of n, something is a black hole microstate. You pick up the value of n and it's no longer a black hole microstate. Well, this exactly matches the fortuity mechanism that's been discovered for 1/16 CPS black hole states. But here there's no SUSY. Yep.
If you change the space-time background, and we changing the boundary field here.
So in n is equal to 4 super Young moles, we can answer that question very, very well. Because in that situation, we have an exact map in the half BPS sector between backgrounds and operators in the CFT. So when you change the background in the gravity and you study gravitons on that new background, you can reproduce all of that physics by having a heavy operator. Then you've got a bunch of light operators. These maybe are the gravitons in your background. And then you have the heavy operator dagger. If you calculate this correlation function, that corresponds to working on the new space-time geometry. This operator here must have a dimension of order n squared. So it must be constructed using n squared fields. And that's why these correlation functions change. You cannot ignore Wick contractions between these light operators and the heavy operators. And the way the CFT computation changes is exactly to match the computation in the gravity on the new spacetime background. But what's important is backgrounds have a dimension of order n squared, and our generic secondary operator will have that property. So the generic secondary operator will be a new spacetime background.
So it corresponds to some like a half BPS state background or something.
So here we don't have any supersymmetry. So I would claim that this is something like take the BMN matrix model at finite temperature, something like that. Dual to that, we know that they are non-supersymmetric black holes. They will have a Hilbert space with this kind of a dimension. You could study some gravitons propagating on that background. If you take one of these secondaries, study this correlation function for that matrix model, you should be able to reproduce the dynamics of the gravitons on that background. So those are the kinds of calculations that we would like to do soon. Yeah. Okay. Now, there is one fly in the ointment. Okay, so well, let me say one thing. We do expect that there's some secondary operators corresponding to solitons, things like giant gravitons. Those should have a dimension of order n, but there's one thing that I should point out that I didn't mention so far, and this is an important effect. If you look at single trace operators with less than or equal to n matrices, those must be included in your generating set. And the reason for that is trace relations haven't kicked in. You need at least n matrices inside the trace before you get any trace relations. So every trace with fewer than n matrices must be included in the generating set. So, okay, I'm going to be a little bit quick on this, but let me just tell you that the number of those operators grows exponentially with the length of the operator. So there are also many, many secondary operators that are short. What are those secondary operators doing? Those are not solitons and they're not new space-time backgrounds. Well, it turns out that when you actually just construct the secondary invariants, you can have, so this is what most of the gravitons of your Fock space start to behave like. You can have a single graviton state. So you were asking about multi-soliton states. You can have a single graviton. Then there will be other secondaries that look like squares of single gravitons or some other products of single gravitons. But there's a cutoff on the occupation number. So the way the trace relations modify supergravity, in supergravity, you expect that you can have any number of gravitons. If the graviton number is unbounded, what we learn from the trace relations is there's a cutoff on the occupation number of these different graviton states.
So when goes to infinity limit, the cutoff will disappear.
Absolutely. So if n goes to infinity, the cutoff disappears. You've just got a free Fock space of gravitons, and all of your black hole states are pushed off to infinity. You don't see them. And this is what goes behind recent claims of people saying it doesn't really make sense to look for black holes in the n is equal to infinity limit. I would say that our results are completely in harmony with that. Yeah. Okay, but this cutoff on the number of gravitons, think about a loop that's UV divergent. What are you doing? You're integrating over all of the momenta inside that loop. Now you find out there's a cutoff. And it's not a cutoff that you put by hand, it's a cutoff because of redundancy. Gravitons with a much higher momentum are not independent of degrees of freedom that you've already summed. This was a redundancy that wasn't recognized in gravity. It comes from the trace relations. Because of ADS-CFT, you must impose a cutoff. This is definitely going to improve the UV properties of the theory. We don't know by how much. We don't know if this is enough to really explain why gravity should be finite, but it will explain the UV properties of the theory. Okay, so here's a summary. Well, I'll leave that there and for you guys to read. So I'll stop here.
So you mentioned that as n goes to infinity limit, also the black holes are going to the infinity and disappear. I'm a little bit puzzling. What does it mean?
Okay, so here is an example. So think about the fortuity mechanism. So before, we thought that if you want to solve for a black hole, you say Q should take your black hole operator and you should solve it equal to 0. This is what you would say for a supersymmetric black hole. We've just found out recently that that is not true. That's not the equation you should solve. The equation that you should solve is Q on your black hole operator is equal to 0 for n is equal to some very special value, n star. But these operators that correspond to black holes, we find that Q on your black hole operator is not equal to 0 if n is bigger than n star. So this is the story of fortuitous operators and fortuity, monotone operators. What you can see is this is really tied to a specific value of n. So this is the only black hole microstates that have been constructed so far, or proposals for them. When you go to higher values of n, I mean, there's this paper of Witten's that has many ideas in it that I'm sure I haven't understood all of it. But he's trying to argue the growth of the Hilbert space is so rapid that thermodynamics in the n tends to infinity limit doesn't make sense. And so he's also advocating that you should have a finite n there. In our story, if you take n to infinity, well, the trace relations disappear because you have to have n matrices inside the trace before you see a trace relation. So the trace relations effectively completely disappear, and your ring is freely generated. So our partition function would look like a 1 over a product of factors, and there's no secondary operators sitting in the numerator. I think that all of these observations are mutually consistent.
There is a very important n side of some magic number.
So you pick an n, and then we can do the physics for that n. But you should pick a finite n.
Some constant n.
But that's true. So you could pick n star as 12, and we could write down the operators. Then you could pick n star as 13, and we could write down the operators again. So the physics will depend a lot on...
I'm giving you a number n star, which is becoming larger and larger.
Fine, as long as you don't take it to infinity. Take it as big as you want, but finite. So the n tends to infinity limit is subtle. That's what the message is.
Any other questions? I have one question. So we know for example, sine-Gordon Thirring duality. So we know sometimes the perturbative degree of freedom is in one model can correspond to non-perturbative. So do you think there's we can think about some primary and secondary dualities?
So that's absolutely possible. So in fact, in a stringy context, you should consider that because there are many known stringy dualities. And what you call a choice of perturbative degree of freedom or choice of non-perturbative degree of freedom, differs on what picture you've chosen. Now, what have we done here? So far I showed you lots of counting results, but I didn't show you many constructions of the different operators. And the reason for that is, although the form, this Hironaka decomposition, is unique, your specific set of primary and secondary invariants is not unique. Your trace relations are a set of constraints, a set of linear equations, and you know that if you've got 10 variables and 20 equations, which 10 variables you keep if you want to eliminate redundancies is up to you. So the actual set of what I call primary and what I call secondary is not unique. And I think there's enough freedom there to realize dualities, swapping perturbative and solitonic degrees of freedom around.
Other questions? Okay, then let's thank the Robert.
Very good. So if you introduce supersymmetry and go to the n equal 4 ADS5, so this kind of main argument still applies.
So Bangun, we are working it out. Let me tell you what is the key difficulty. So these math results They have both of the bosonic matrices.
Right. So fragment is
So
the
now you look at the Grassland matrices. And for example, things like what does Cohen-Macaulay mean? What does adenine adaptive group mean? All of those things need to be repeated. But funnily enough, the real hardcore mathematics that work on a invariant are now working on Earth. So there will soon be results coming from them.
okay, but I can just accepting the supersymmetry, but I can only restrict to the bosonic sector.
Then if you restrict, okay, so if you restrict just the ground even, there's a result for that. In that case, the ring of invariance is known to be Cohen-Macaulay. So there is a Hiranaka competition.
I see.
So that
The spins and those things are some minor thing. Like we have a scalars and the vector fields and the gauge theories.
So, to be honest, what we keep doing is we keep looking at limits of energy for super moles when things reduce to quantum mechanics just of matrices. Your question is very fascinating, but it means making sense actually of the field theory. And so far we don't know how to do that. But we have done one thing. Strominger had this conjecture about how to do DS CFT.
Okay.
And he was relating some symplectic vector model, but he got it from a bosonic vector model.
Okay.
And there was meant to be a duality between the two, some analytic continuation. We took these two models, we put them both on a lattice, and we can now see a duality between the dimension
Like
of the
Owen vector model.
Owen vector model. We can now see a duality, an exact match between the dimension of the Hilbert space in the de Sitter description and the number of secondaries in the bosonic description. So that feels like it's the right kind of a thing. So how did we get that? We were studying a field theory, but we put it on a lattice, and it seems that all of these nice features survive. You're never sure if you put something on a lattice, what are you going to make up? Seems like you can still ask these kinds of questions.